Demonstration of AiiDA workflows. In our work as computational material scientists, we rarely execute a single calculation to get our answer, but mostly our work consists of multiple steps that operate on input to get to an answer. And this paradigm is implemented in the shape of workflows in AiiDA. In this example, we'll show you an equation of state and how to compute this. AiiDA calls these workflows work chains, and we'll show you how to define such a work chain. So in our case, we have called it equation of state, which, as you can see, is a type of work chain. And the most important method of this class is the define method. The define method will, as the name suggests, define all the inputs that it requires, and then it will specify what it's going to do with those results to finally get to the outputs. So first we'll take a look at the inputs. Each input is defined by calling spec.input, and we'll provide a label or a name, and it will also tell you what kind of valid data type it expects. So this will automatically take care of the data validation. So as you can see, there's 4 inputs that we require. We require a beginning structure, a code name that we'll use to calculate the equation of states, a pseudo potential family, and the number of points that we would like to plot. The next step is the outline, and the outline defines the number of the sequence of steps, or the business logic that will operate on the inputs that are provided. So each of these class methods will be implemented further down, but this will give a nice overview of what we expect it to do. So we have some initialization function, and then we'll have a while loop. And as you can see, this is basically very close to normal Python logic. And so while this condition is true, while we want to run a self-consistent PW calculation, we run it, and then we parse the results. And when this is done, we analyze the final result. And in the end, we will have a dynamic output. So now we can actually see the implementation of these methods. So like I said, in the init methods, we set some beginning data, for example, the K points and the inputs for the SCF calculations. And we also set up a plot in this case. Then our main condition is whether we should still run our PW, which will basically check if we have computed all the points that we requested and thus nothing more. The actual run PW calculation will create the inputs for it and launch. Here we'll see PW calculation. It will run it and attach it to the context of the work chain. In the parse PW steps, we'll simply look for the volume and the energy, because that's the 2 quantities that we'll plot. And in the end return result, we will we take the final structure and the final result, which is the energies as a function of the volume. So if we execute this, we've defined our work chain. Now we would like to actually run it. So we'll first need to provide a structure. In this case, we're going to do diamonds. So we define, this is a helper function that will create the structure for us. All it needs to know is the element, in this case carbon, and the lattice parameter. We also define our code name and the pseudo potential family that are already pre-installed in our system. And then to run the equation of state, we simply provide to the run function, we provide the class name and the 4 inputs that we have defined in the definition. And when we run this, it will dynamically start plotting the results. So now it will do multiple PW calculations, and as they become available, as they have been calculated, we'll take the result and plot the computed energy as a function of the volume. And so as you can see now, step by step, this plot will become filled, and these since we asked for 5 points in the inputs, it will plot 5 points. But of course, you can change the input and make this more dense. So this is the demonstration of how work chains work in AiiDA.